All right, section 6.1 is the set of rational numbers. And we're going to start in with sort of defining what that means. What does rational numbers mean? All right, so rational numbers are any numbers of the form a over b, where a over b are integers. And you've probably commonly called them fractions, and when you've said the word fractions, you've actually meant rational numbers. There's just a slight difference. Fractions don't have this extra condition right here that rational numbers do. Now, most of the fractions you've probably worked with have that true about them, and they are fractions. But there are some fractions that don't have integers on the top or the bottom. Have any of you ever taken trig or geometry? Okay, and have you had something called pi that you've worked with? Pi is not a rational number, it's irrational. It's really not 3.14, I promise. Contrary to popular belief, it is not 3.14. That's an approximation for it. So anytime you've got a pi involved in something, which you often do in those two particular courses, it would not be a rational number. It would be a fraction potentially, but not rational. So we do actually have to have integers on top and bottom, or the ability to turn something into an integer, and we'll see those kinds of things happen later. What is the numerator if we've got this fraction a over b? The top, which is a in this particular one, right? And then the denominator would be the bottom, it would be b. Now there's several uses for fractions, or for rational numbers specifically. One is in solving equations like 2x equals 1. So if you just had integers and you were trying to solve this, and you let x equals 0, you'd end up with 0 on the left and 1 on the right, which doesn't work. But then as soon as you let x be one number bigger, x equals 1, then you get 2 on the left and 1 on the right. Also doesn't work. So the answer is somewhere between 0 and 1, which means we need a value between those. Well, there aren't any integers between 0 and 1, so we need a new value that we call a rational number, specifically a decimal or a fraction. Chapter 6 is going to work with decimals, so everything we do in this chapter is going to be working. I'm sorry, I said it wrong. Chapter 6 is going to be working with fractions. Everything we do in this chapter is going to be in terms of fractions. And then Chapter 7, we're going to work with decimals. So we are going to treat them sort of separately right now, and we will blend them when we get to Chapter 7 a little bit too. But for right now, just fractions, okay? Another possibility is a partition use. So a partition is something like this, where we talk about 1/4 of my income pays for my car. Okay, it's a portion of something else. 1/4 of it, 1/4. Of course, that 1/4 is a decimal, and it's a percentage, and it's a fraction, and it has all those meanings, but that's understood to be a partition or a portion of something else. Another use is in terms of ratios, something like this. The teacher to student ratio is 1:8. Okay, and we can write that in a fractional sense as well, 1/8. We can write that in this notation as 1:8. But it's a ratio. It's a comparison of two things is what you're really doing, comparing the number of teachers in this case to the number of students. And then a fourth way to think about it, or a fourth use for rational numbers, is with probability. Probability is when we talk about how likely something is to happen. It's going to be very likely, it's going to be not very likely, those kinds of things. So something like this, when you roll a die, you have a 1/6, 1/6 chance or probability of rolling a 4. And it doesn't have to be in just chance games. We can talk about probability when they talk about weather forecasts too, right? You've got a 60% chance of rain. Well, 60% can be understood as 60 out of 100, right? That's a fraction. It's a rational number. So we use those not just in concrete game kind of play, but we use them in other situations as well. All right, so what we're going to do next is we're going to write fractions for some pictures. So I'm going to draw some pictures. So I'm going to draw 4 pictures, shade them in and everything. So just do that, copy them first, and then I want you to do your best to try and figure out what the 4 probabilities, or fractions are that they represent. So give me just a little bit while I draw my pictures. Come on. And they're not perfect. Pretend for the moment like they are, okay? Just pretend that they were drawn perfectly. So this is A. I'm getting close. I did want those there. All right, we'll go with that picture. That'll work. Okay, in the first picture, you've already had that one written down since I drew that one earlier. How much of the diagram, again, if it were drawn perfectly, is shaded in?
1/6.
That is 1/6. So any guess as to what a child might do when they look at that would give you an error? They might say 1/4. So if they said 1/4, what would they be sort of erring and thinking?
That they're all equal. Like each little quadrant is the same amount.
Yes. Now, that's the error they're making. What are they thinking when they're doing it, though? They aren't actually thinking that at all.
Like counting the boxes.
They're just counting the boxes, right? They're looking at the boxes and they're just saying, hey, I have 1 box that's red. This is actually red on my screen. And I have 4 boxes total, so it's 1 out of 4. That would be a very common error. So we could talk about it just like Rachel just said and talk about the fact that, yes, but the boxes need to be the same size. In fact, in this diagram to help the students out, what you might even do is you might even draw in the additional lines here that are sort of missing, quote unquote, so you can see we really have 6 equal sizes of shapes, and so we have a 1 out of 6 shaded in instead. Same kind of idea is really going on in part B. What is this one going to be? 1/4. And even kids who might have gotten part A right might miss part B, but for the exact same reason, right? The boxes actually almost look the same size. They're a lot closer than they were on part A. But again, the point is how much is shaded in. And so we have to talk about, equal size boxes. So we could actually sort of change this right here into making the boxes the same size, based on the one that's already shaded, which is that red corner, one in the bottom corner. What about this one on part C? 1/3. What would you probably see kids do first? 2/6. I'm sorry, 2/3. Yes, 2/6. I said it right the first time. 2/6, which is convenient and easy. This actually has a really nice imagery because you can talk about pizzas or pies or something like that. So you've got 2 out of 6 pieces. This also makes it a nice argument for them to talk about. Yes, that's true. And if we sort of change this to having the pieces look something like this instead, you can see how we have 3 larger sized areas and 1 of the 3 shaded in. So you can draw really nice comparison pictures for kind of justifying why we're able to do something called reducing fractions, which is nice. So we can talk about this being either 2/6 or 1/3, depending on what we're focusing on in the work we're doing with the kids, actually. What about part D? What do we have on that one? What is it? 7/12. Part D is very different than the other 3 diagrams. What's different about D than the other 3? They're separated. All of the other 3 are sort of parts of a whole, right? They're a portion of something that's a complete unit of value of 1 or something like that. This kind of a diagram is something different, and it works really well to use. Coins would be an example of something that you could talk about this way. Actual physical objects that are their own objects, right? Like I have, in this case I could talk about 12. I have 12 strawberries and I eat 7 of them, so I've eaten 7 out of 12. Those kinds of things where the actual object is the whole instead of the whole being something that you've eaten part of something or taken away part of something else. Okay, a couple of historical notes about fractions. Fractions have been around for a very long time, used in a variety of contexts. Egyptians used fractions, but all of their fractions had numerator 1. So that last example where we had a 7 out of 12, they wouldn't write 7 out of 12. They would have written the 7 out of 12 as 1/4 plus 1/3. So they would have written it as a sum of 2 values that each had a numerator of 1. Now if we actually added this together, you would find out fairly quickly that that really is 7 out of 12. But there's a little awkwardness in representing it that way. At least I would feel like that's very awkward to have that sort of extra condition upon fractions. The Greeks adopted fractions, but they used denominators of 60, and they did it from the Babylonians. And this sort of a description is still used in measurements of angles today, and not necessarily angles like angles of a triangle per se. But we do use measurements of angles of 60 and sort of units of 60 in another place as well. Where else do you see units of 60 used in this sort of awkward way? What is it? Minutes. Minutes and seconds use this idea, right? So we have 60 seconds in 1 minute. We have 60 minutes in 1 hour. That kind of a fraction of a time length is often used with minutes and seconds. The Hindus developed our modern bar between the numerator and denominator, that horizontal bar that you see drawn. Please use the horizontal bar and don't use the sideways bar. It's really easy when you're doing a sideways bar for something like this to turn into looking something an awful lot like this, which has different meanings. But if you're drawing it like this, it's much less likely to happen. So please draw the bar horizontally because it's a little bit clearer. Okay, the Hindu are the ones that did that, and that was in the early 1500s. And we're going to take a look at some different area models, and we've already seen these used to some extent back on the very first example we did. One model is the area model, and that is where we've got a portion of something in terms of its area shaded in. And a good example of that is a rectangle, although you could use a circle as well, but a rectangle works very nicely. And so you can talk about, for instance, what do I have written down? 3 out of 4 of a rectangle being shaded in, and it's an amount of area or amount of space. So we can split our diagram into 4 pieces, and then we would shade in 3 of them. So this would be 3/4 of the room has my stuff, and 1/4 of the room is your stuff. 3/4 of the garden is strawberries, and 1/4 of the garden is bell peppers, something like that. All right, so a number line model is another another model that demonstrates this very well. So number line model, we'll use that same example of 3 over 4, is the idea that if I have, it's black here, if I have a line set up where I start at 0 and I end at 1, then I can split it in half, I can split it into fourths, and the number 3 over 4 would be a portion of the way between 0 and 1. And, you know, we talk about this kind of a description all the time. I'm halfway there. You know, I'm 3/4 of the way there. I'm 5, we say some things with minutes, but I'm 5 minutes away out of a 15-minute trip or something like that. I'm 1/3 of the way there. So we don't always call the ends of them 0 and 1, but we use this kind of framework for our fractions all the time. And the last one is a set model, which you saw me use as well with those chips that were shaded in. That's called a set model. Use of chips are congruent circles where some are shaded in. And so again, if we had 3 over 4, the easiest way to draw a set model would be then to draw draw 4 chips and shade 3 of men. All right, there's my 4 chips and shade 3 of men. Now, that can always be done if you're working from scratch, right? If I give you a fraction and I told you to create a set model, you could draw me, the denominator has 4 pieces, the numerator would be telling me to shade in 3 of them. That works just fine. But the set model has limitations. What if you were working with money and you actually had 5 quarters? And somebody says, I want you to give me 3/4 of them. That's awkward. I mean, what are we supposed to do? Like cut a coin in half or something? I mean, like that's a very awkward sort of thing. So this statement about being limited or having limitations is about that. If you have an object that is a whole, you can always split that whole into a certain number of pieces. But if you're working with something that already has individual pieces in it, it may or may not be convenient or easy to actually split it into the number of denominator pieces you're supposed to have. And that's a little bit awkward. So that does have some limitations to it. All right, working with a few theorems about fractions. The first one, if we have a fraction a over b, and we have any non-zero integer, then if we multiply the numerator by that value and the denominator by that value, the fraction stays the same. Right, so the idea being that if you had, for instance, 1 over 4, and you multiply the numerator by 2 and the denominator by 2, which would give me 2 over 8, that would be exactly the same amount that I originally had, just expressed differently. Okay. And of course, the same works going backwards. It's not just multiplication. In fact, you could do it with division as well. If you can divide the numerator by 2 and divide the denominator by 2, it keeps things equal as well. Now, simplest form is the idea of changing your fraction into something where the numerator and the denominator don't have any factors in common. So in elementary math 1, one of the things we learn about is this thing called a GCD. And you guys have used this before, even if you haven't taken that class. It's called the greatest common divisor, or sometimes it's called the greatest common factor. And the idea is that you're looking for in the number if the numerator and denominator are both divisible by the same number. They're always both divisible by 1, but we want something sort of bigger than 1 that they're divisible by. For instance, if we started out with the 2 over 8 from the piece of example above, we could say, hey, look, they're both even. Well, since they're both even, I know they can both divide by 2. And since I can divide them both by 2, I can reduce this fraction to 1 over 4. If you get a 1 anywhere, you know you're done reducing. Or if you just get numbers that you know don't have anything in common, you're done reducing. So this idea of simplest form having no common factors that are bigger than 1. All right, so we're going to do an example with that kind of a feel to it. We've got the fraction 3 over negative 14. I know it's kind of small, but you do have it written on your paper. Hopefully it's a little bit readable there. 3 over negative 14. Somebody tell me one example of a fraction that would be equivalent to the fraction 3 over negative 14? Give me an example.
6 over negative 28.
All right. So Lacey, how did you get to 6 over negative 28?
I just multiplied it up by 2.
Perfect. You can multiply the top and the bottom by 2. Another example.
Negative 3 over 14.
Perfect. I usually don't have people think of that one, but that's a perfect example. So tell us what you did to get that one, Shelby.
I just multiplied by negative 1.
Yeah, we can multiply the top and the bottom by any value, positive or negative, right? I mean, it was an integer, and negative 1 works fine. So it may not really look to you like that's really any different, but it is. I mean, negative 3 over 14 is a different fraction, or a different way of representing that fraction. All right, one more.
9 over negative 42.
Okay, and how did you get 9 over negative 42, Abby? Okay, so you can multiply by 3. So there's infinitely many options we could get here, right? I mean, yours doesn't have to look like mine, and they could all be correct. Okay, great. Now, this one down here asks us to find the simplest form, but it does something a little bit different. Do you see how this says, I'll write it a little bit bigger, squared? So it's a little bit tempting to sort of just like cancel out the squareds. That would not be correct. You can't do that. There's no property that allows that. But what we could do is we could write that, instead of writing it as squared, we could write it as multiplication. So we could write this instead as something like 42 times 42 over 35 times 35. That would be perfectly acceptable, okay? All right, but we're looking for things that divide into the numerator and the denominator. So somebody give me something you see that divides into both. 7. And we can do it twice, actually, can't we? So I can divide 42 by 7. So what's 42 divided by 7? 6. And then what's 35 divided by 7? 5. So that was dividing the numerator and the denominator by 7. I mean, I recognize we didn't divide the other 42 and the other 35. We still need to do those. But we did it once, so we can do it again. So now I can divide this 42 by 7 to give me, and this 35 by 7 to give me. All right, great. So now all I've got left on top are 6's, and all I've got left on bottom are 5's. And I mean, they're multiplied, right? It's 6 times 6, and it's 5 times 5. But is there any more simplifying that we can do between 6's and 5's? No, they don't have any numbers besides 1 that divide both of them, right? So the best we can do at this point is to simply multiply what's left and write it over what's left on bottom. So what's left on top? 36. And on bottom? 25. Now, this is a good opportunity for us to talk a little bit about what your answer should look like at the end of a problem. At the end of the problem, your answer should be in the same form the problem started, unless you're supposed to be converting something. Like if the problem says, put it in an improper fraction, or put it in a mixed number, or turn it into a decimal, then you need to do those directions. But if there aren't anything indicated on how the answer should look, if the answer looked improper to start with, it should look improper to end with. If it looked like a mixed number to start with, it should look like a mixed number to end with. This problem looked like an improper fraction to start with. It already had 42 on top of 35. So this answer of 36 over 25 is completely fine just as it is. Okay? All right. Next thing, we have several ways to determine if fractions are equal. One way to determine it is to take a look at it as though we've got an equal sign between them, and we do something that you've probably heard called cross multiplying. You guys remember that? Where you say A times D, so we get this AD over here, equals B times C over here. And if in fact A times D really is equal to B times C, then we have the original fractions equal as well. That's one way to determine if fractions are equal. Does anybody remember another way? There's at least 2 more ways. Without turning anything into decimals, that is not what I'm talking about.
Finding a common denominator?
Yeah, a common denominator is a really good way of doing that. And it doesn't even have to be a common denominator, Rachel. It could be a common numerator. But if you've got a piece of something that's already equal, then obviously when you cross multiply, things are not going to be the same unless the other piece was equal too. So yeah, if you had a common denominator or even a common numerator, we could make a claim about something pretty quickly. And sometimes people will classify a common denominator as being different. We can find a common denominator, or we can find a least common denominator, which is just more of a specific kind of denominator. So let's take a look at these examples. We're going to find several ways to determine if these are equal. So one option is exactly what theorem 6.2 or 6-2 above says, which we could do cross multiplication. So let's do that one first, okay? So option number 1 for determining if these are equal. First of all, they're both negative. So can I just ignore the negatives? Are you guys good with that? All right. So we've got 3 over 12. And we're testing, question mark, is this going to be equal to 36 over 144? And one way we can do that is by doing cross multiplication. So if we cross multiply, what is 3 times 144? 432. And what is 12 times 36? 432. So since the result down here is equal, then the original two fractions were equal as well. Okay. That's not too bad, but I would probably wager that nobody actually did that multiplication in your head, right? You either did it on a calculator or you had to long multiply it out by hand, depending on what you're sort of working on in the process. So if the fractions were smaller numbers, this works really well. But if you are in a classroom that's not using calculators, which is probably where most of you are going to be, if you're teaching, grades, pre-K up to about 5th grade or whatever, then asking a student to multiply these out might not be, they may not be very friendly towards you. That doesn't sound like a very fun idea. I don't want to multiply 144. I would really not want to multiply 12 by 36, more than the other one even. So another option in determining if they're equal would be to do something with the denominators the same. So let's do number 2, and actually there's a third option that I haven't mentioned too, but let's do number 2, which is going to be finding a least common denominator, because it keeps things small. So I've got 3 over 12. Question mark is, does it equal 36 over 144? So finding a least common denominator means you're comparing the denominators you already have. And you're sort of asking yourself, is there a way to get these denominators to be the same with the least amount possible of multiplication? When you compare 12 and 144, if you know multiplication tables to 12s, which are usually what you're learning in about 3rd grade, you recognize that what would you need to do?
Multiply by 12.
Multiply the first denominator by 12, right? So if we multiply the first denominator by 12, what does that mean we have to also do? Multiply the first numerator by 12. So we multiply both the numerator and the denominator by the same number. So this gives me 36, in fact, over 144. And lo and behold, what do you see? They are equal. So yes, the answer would be that they are equal. Now sometimes, this one was pretty nice and clean. I mean, 12 and 144, you can compare this pretty nice. Sometimes denominators are not easy to compare like that. They simply don't have anything in common, maybe. Or maybe they have some things in common, but not the whole thing in common, right? So a third option, number 3, we'll say, is to find a common denominator. Notice I did not use the letter L with that, correct? So this is not a least common denominator that we're going to look at. We're just going to look at a common denominator. Again, this was a process that will work a lot better if you're working with smaller numbers. Okay, so I'm about to show you something that's not particularly helpful with big numbers, and I'm working with big numbers, so I apologize for that in advance. But the idea is that if you can't identify quickly what the least common denominator is, you can at least get a common denominator simply by multiplying the two denominators together. No matter what they are, that will work. So if I multiply the first denominator by 144 and then its corresponding numerator, and the second denominator by 140, which is 144, by the 12 and its corresponding numerator, I will in fact get the same denominator. I mean, like, it has to work, right? They're 144 times 12, both of them. They're big numbers, so that's not especially friendly. But what do you get? You guys got calculators with you, at least some of you do. What do you have? What's 144 times 12? 1,728. And they're the same on both sides. So somebody multiply 144 times 3 for me. I think we already did that once today. 432. Somebody else Do the 36 times 12. I think we did that today too. 432. Again, I'm not saying that this is a particularly friendly way to do everything all the time, but it is an option when it works nicely. Smaller numbers it works more nicely for. There is one other option that will often work. Again, and this option actually works really well when the numbers are larger. So that's friendly because we've got larger numbers on this one. This one right here is to reduce the fractions. So, taking a look at 12, sorry, 3 over 12, I wrote it wrong. 3 over 12 and 36 over 144. You might do one of two things. You might simply notice again that the second denominator, 144, has a 12 in it. I mean, you could do that. So in other words, you're sort of taking a look at this and you're saying, these are both divisible by 12. So if I do that, 36 divided by 12 is 3, and 144 divided by 12 is 12. And at that point, of course, the two fractions are the same, and that's fantastic. Now, they aren't actually reduced, either of them. They could reduce further, but that's really not the question asked, right? The question asked if they were the same. So at this point, since we got them the same, we could stop. If you had sort of been reducing the far one on the left already into 1 over 4, which is what it reduces to, then you would have to keep going on the right-hand side for the same reason. But at the point, once you get to the point where they actually match, then you know they're equal. So there's 4 ways of changing fractions around or checking to see if fractions are equal. All right, so aside from being equal, we could also have fractions where one of them is larger than another one. Okay, so comparing the size in terms of inequalities instead of inequality between them. So if a, b, and c are integers, and we have the fraction a over b and the fraction c over b, notice these denominators are the same right here, right? A over b, c over b. And the first fraction is bigger than the second fraction, then it means the numerator of the first fraction is bigger than the numerator of the second fraction. All right, like imagine that you had a pizza and it had 8 pieces. I eat 2 pieces, you eat 3 pieces. Well, obviously, you ate more. 3 is more than 2. So 3 out of 8 would be more than 2 out of 8. I mean, that's what you're saying here. If the denominators match already, you can simply look at the numerators to make a decision. Now, another thing happens, though, when we have the denominators that are different, right? One of these denominators is b and the other denominator is d. Well, it's a lot more complicated to compare something, for instance, like 1 over 4. Hang on, let me do a bigger number. Let's say 3 over 8 and 2 over 6. I mean, the numerators and the denominators are different. You know, and especially on the first one, the numerator is bigger and the denominator is bigger. That's not convenient to compare. So drawing a picture could be very helpful. I mean, that would be a legitimate argument. You could draw a picture and make an argument about which one's bigger. You have to just make sure that your pictures are the same size, that you've divided things evenly, and compare them well. And it helps also when you're drawing a picture to argue, especially to argue that this actually works with a child, to do it in such a way that you're doing it with a rectangle. Let me show you what I mean. So if you're doing this rectangle, I have 2 rectangles that are the same length. All right? So the first one is supposed to be split into 8 equal pieces, and you'll probably do better on paper than I'm doing on the board. Oh, you know what? That's not too bad. And so here's 8 equal pieces, or at least pretty close. And then the second one splits in half just the same, but then it splits into 6 equal pieces. And so I shade in the first 3. I shade in the first 2. And then if we've drawn them carefully enough, we should be able to make a claim on this one that it would appear that the first one is bigger than the second one, right? If I've drawn it well. Because the first one's shaded further along. Let me draw this in a different color. If I've drawn it well, this one, I know that's not quite straight, but this one on the top is shaded further in than the one on the bottom. Okay, again, you have to be careful with the drawing, but you can make that argument pretty well with pictures. Now, the theorem itself says that what we can do is we can use this same kind of cross-multiplying idea. So I can multiply a times d to get the AD. and I can multiply b times c to get bc, and then the inequality stays the same direction. And all of that works as long as the numbers themselves are bigger than 0. Notice it says right here that B and D are positive. And even up here it says it as well, B is positive. If B or D is negative, everything reverses direction. Everything has to change. So it's only if the denominators are positive that's going to work. So the easiest thing to do is to simply let, if the fraction's negative, simply let the numerator be the negative part and ignore the denominator being negative. So that's an easy way to fix that. All right, so we're going to take a look at this one. This one wants us to put this in ascending order. And we can do cross multiplication if you want, but it's not especially friendly on this problem. Any guess as to why? What's that, Shelby? The different denominators isn't going to make that unfriendly. I mean, you're right, they don't have the same denominator. The 20 is kind of large. Still not quite what I'm going for. There's 3 of them. Yeah, that last theorem is really helpful when you're comparing 2 fractions, but this one's got 3 fractions. And in order to make that last theorem work, we'd have to sort of take them 2 at a time and do a comparison, and it would get a little bit convoluted pretty quickly. There's another thing that makes this one easier to do in a different way. Yeah, those denominators are pretty convenient to find a common denominator between. What would a common denominator of all 3 of them be? 20 works really well. So I can take 13 over 20, and I don't have to do anything to it. I can take 3 over 5. What would I need to do to the 5 to get it to have a common denominator with the 20? Right. And if I multiply the denominator by 4, I have to multiply the numerator by 4. So what does this fraction become? 12 over 20. Exactly. Very good. And then we have one more. We have 7 over 20. I'm sorry, 7 over 10. What would I have to do with this one? Yeah, I need to multiply times 2 on the top and bottom, which would give me the fraction what? 14 over 20. Okay, so it says ascending. What does the word ascending mean? Yeah, smallest to largest. That's what ascending means. Descending means the other direction. So which one's the smallest? Oh, and I'm so glad you said it in that way. It is 3 over 5 because that's the way the question was given to us. Okay, so while 12 over 20 is also a correct value, it's not the way the problem was given to us. So we're going to use 3 over 5. What's the next one that's the next largest? 13 over 20. If you want, you can put a comma here and write 13 over 20. If you want, you can put a less than sign and put the 13 over 20. It doesn't matter, but you could use either one of them. I'll be consistent and use the same thing. And then the largest one then would be 7 over 10. Exactly. Excellent. Now on number 2, or example 4, the second one on the slide, it wants us to use a less than, greater than, or equal to, one of those 3 symbols to go between them. We can use any of these methods we've chosen before. We can find common denominators, we can reduce things, we can find a least common denominator, we can cross multiply, we get to pick. So somebody tell me what you would like to do with this particular problem.
Common denominator.
Common denominator. Okay, Rachel, what do you want the common denominator to be?
430.
Okay, so how are we going to get that to happen?
Just multiply the second fraction by 2.
Excellent. So on this one, a common denominator jumped out to you. You looked at it and said, hey, I see something here that's going to make this easy to work with. Sometimes that happens, and sometimes it doesn't. So there's not a right or a wrong. It's just good to have some options. So if we do that, the first one stayed 21 over 430. What does the second one become?
1 over 2 over 430.
1 over 2 over 430. So which symbol goes between these? Less than. The one on the right-hand side's bigger, so the opening is towards the right-hand side. Yes? Okay. Also, if you take a look at just by comparison, this one right here had a bigger numerator and a smaller denominator. If you've got something bigger on top, it's generally bigger, and smaller on bottom, it's generally bigger. So that seems to make sense sort of in a reasonable way as well, if you're thinking through just the reasonableness of what we've done. Okay. I think we have time for one more slide we'll talk about and the example for it, and then we'll stop for today. The denseness property for rational numbers says the following. If you have two fractions, there has to be something in between them, and it's also going to be a fraction. There's going to be a fraction at least in between them. In fact, the easiest one to get is the one halfway between them. That's most convenient. But there's always going to be infinitely many fractions between them, no matter how close they are together. And if you sort of have this idea in mind of that number line point of view that we talked about before, if you think about what happens, and you guys have seen this happen on your calculators before, you have the ability to sort of zoom in on the calculator, and what it does is it sort of looks like it spreads things out, right? That's the image. No matter how close they are, you could keep zooming in and it would spread out the image on your screen, and there would be space between. Well, space between means numbers between. And that's all the denseness property says. Now, as a result of that property, there are a couple of ways you can find a number between. One option is just to add the two numbers together, divide by 2. It's called a midpoint, something halfway between, or an average value. Okay, add something together, divide by 2. And that's fine. It works fine. It's a little bit complicated sometimes if you're already dealing with fractions, especially if the fractions don't have the same denominator. You're going to add two fractions together that don't have the same denominator. And after you add them together, then you're going to divide by 2. That could be pretty messy. Agreed? So this denseness property sort of lends itself to another option. And I think this is a really cool one. So here's A over B and C over D. They are different denominator fractions. What you can do is you can add the numerators together, add the denominators together, and that will result in a fraction, not halfway between them necessarily, but it will be between the two numbers you started with. Sometimes it's halfway. It depends on the numbers you're working with. That's pretty cool. All right, and that's a pretty nice feature. So let's just do a real quick example of that. I have that on the next slide. Yeah. 33 over 427 and 34 over 427. These two actually have the same denominator. But there is no space, so to speak, in terms of numbers between 33 and 34. Now, we could say 33 and a half, and that's okay, except that that's not in rational number form because 33 and a half is not an integer. Everybody with me so far? So we can use this rational number property, and we can actually add 33 plus 34 and 427 plus 427. So the denominators don't have to be different to make this work. They could be the same. That'd be all right. And if we add them together, what is 33 plus 34? 67. And 427 plus 427? 854. And it doesn't get much simpler than finding that value. I mean, add those together, divide by 2 is going to take more work. I mean, and you would actually end up with the same kind of an answer, right? A number between them. So, real quick, let's write this in right here below. Why does this work? Why must there be a number between these numbers? That should say there. Why must there be a number between these fractions? Can you guys write something down for me? What do you think? Why must there be a number between 33 over 427 and 34 over 427? Yeah, there's always space, right? And because there's a space between two numbers, they aren't exactly in the same location, there is a number between those that represents that location in space. And that's what the denseness property says. So you could actually talk about, because of the denseness property. I mean, that's what the previous slide actually said. The denseness property says there is always space between two non-equal numbers. Obviously, this wouldn't work if the two numbers were equal to start with, but they have to be two non-equal numbers. Hence, there is a number associated with each point or location, you could say, in that, I'll use the word between space. That space that's between.